Welcome to Arcade Labs. Today we're going to be doing some additional work on this Atari Battlezone Cabaret. Previously we replaced the right-hand joystick bezel as well as the fluorescent bulb for the marquee. Today we're going to be taking a look at the monitor itself. Despite the brightness being turned all the way up, the picture is still fairly dim. It might look okay in the video here, but in person it's actually fairly dim and it makes it difficult to play. So we're going to pull the monitor out and diagnose what's wrong with it. All right, let's get into it. I've taken the back off the game and we can now see the monitor is right up here. One thing about this cabinet is that this piece here blocks the monitor, so unfortunately we can't take the monitor out the back like we would normally on a full-size cabinet. So the monitor is going to have to come out through the front of the cabinet, and we'll be loosening some bolts right here and here, and then we should be able to slide it on out. One other thing about this blocking the monitor is that I'm not going to be able to discharge the monitor before removing it, so I'll have to be careful not to touch anything in the back here until I get it onto the bench. We're going to disconnect the wiring harness from the monitor, and then we're going to remove these bolts that are holding it to the cabinet. There's one. And two. The first step to opening up the front is to remove this bracket up here that holds the plexiglass to the front. All right, we got the bracket off, and here's the plexiglass, and that's actually pretty dirty. We'll have to wash that. The next step is to remove this paper bezel, which is actually fairly fragile. I don't know that you can even get replacements for this, so I'm going to try to be very careful. It is currently held on with electrical tape, which is interesting. I'm not sure how these were originally held on. All right, so we're taking this off. On the front of the monitor here, we have what's called gels. It's basically a plastic film that's kind of taped across the monitor. So we have like a green section and there's a red strip up here. And this is what actually gives the color to the game, because this is just a black and white vector monitor. So this top part, this film makes it red, and the bottom gives it the green look. To get the monitor out, we have to get these joysticks out of the way. So I've removed the two carriage bolts here, and so now we can basically just rotate the joysticks out of the way, and this will give us fairly good access here to the monitor. This monitor is not super heavy, so this should be not too hard to get out, I hope. Gotta be careful not to bang it on anything. All right, we got the monitor on the table here next to the game. This is what I was referring to about the gels. This is a red filter, and then we got a green filter down here that gives the color to the monitor. We can take a quick look inside, see what we've got going on here. That's interesting. The anode suction cup, it looks like it's not fully inserted into the tube. All right, we're going to use a high voltage probe to discharge the monitor. I'm going to connect the ground lead to the chassis, and then we're going to stick the other end down here into the anode. I see on the side of the monitor there's some handwritten notes. Someone has written 15V2000, which is referring to the model of the Wells Gardner monitor. On the bottom of the chassis, we've got 4 power transistors, such as a 2N3716, and these are mounted directly on the chassis, and they use the chassis as the heatsink. One thing I've noticed is that there's heatsink compound kind of coming out of several of these, and that tells me that they've probably been replaced at some point in the past. I've got the monitor turned around here on the table and I have it plugged into the game. It's nice that the cable is long enough to reach so we can run the monitor while it's on the bench here. Let's go ahead and turn this on, and we can then go around and check and see what it looks like. This monitor takes quite a bit of time to warm up and start showing an image, more than a lot of my other vector games. Okay, so we can see we've got the display. One of the interesting things about this is that the foreground, like that game over and press start, is actually pretty bright, but it's all of the background, the mountains, the obstacles, and like the enemies are all muted. And so we need to figure out a way to get that bright again. That's kind of the main problem. I previously mentioned that the anode suction cup didn't seem to be securely on the side of the monitor. And so now when I look at it, I can see that it looks like one half of like the anode clip is not in the monitor. So this could be affecting our picture. After fixing the loose anode cup, the lower intensity vector lines do look a little bit better. A better test might be to put the smoky plexiglass in front and then see how it looks. So with the plexiglass in place, it kind of looks like we're back to where we started from, maybe a little bit better. In a dark room, the screen looks pretty good, but the game should be playable in a room that has some medium ambient light. Alright, I've removed the screws and unplugged all the cables to the deflection board, so we're going to take it out and take a look at it here on the bench. The board looks like it's in reasonable shape. We've got 5 fuses on the board here and over here. Here is the brightness control, and that's the contrast control. So we're going to be testing those to make sure those are good. Alright, I've spent some time inspecting the bottom side of the board and gone through, and anything that looks suspicious I have gone through and pushed on the solder connections to see if anything is loose or has moved. And so I found a few problematic areas. The first one is right here. Let me see if I can zoom in more on that. So right here, this lead for this diode is coming through the board, and I can actually move it back and forth. It looks like we're completely missing the solder that should be soldering the lead to this trace. So that needs to be fixed. Right here is another case where it looks like we're missing solder. I'm not sure if it's breaking the connection or not, but we're going to fix that. And then down here, we also have a case where I have a lead poking through the board, and I can move it back and forth, so it's definitely not soldered to the board. I don't know if the solder just fell off. This was just a cold solder joint, but we're going to have to fix that one too. Alright, we'll start with this one right here. Okay. Now we'll move on to these guys down here. And this one is particularly bad. There's absolutely no solder connecting this to the board. The next thing we're going to check is the brightness potentiometer right here. And this controls the brightness of the screen. And one thing I've noticed is that when it's turned all the way up, which is the way I had it earlier, we don't see any retrace lines on the vector screen. And usually if you turn the brightness all the way up, you'll get extra lines where the vector beam is moving from one place to another. So that could indicate that we're not getting the full range on this potentiometer here. This is supposed to be, I think, 100,000 ohm potentiometer. So in one extreme range, probably counterclockwise, it's going to be 100 ohms, and then the other direction it's going to be 0 ohms. So we'll go ahead and measure it in circuit here and see what we get. So I'm going to put one lead down here on the wiper terminal, and then we'll see what we get on the other two here. One of these should be the maximum and one should be the minimum. So we're getting almost 500 ohms there, which is not what I would expect. And then over here, we've got 61k ohms, which is also not what I expect. But since it's in circuit, that might be why we're getting that. But I would expect this one over here to be 0 ohms, and we're at almost 500 ohms. So this might mean that our brightness is not going all the way up and this potentiometer isn't functioning correctly. All right, I've got the board installed back in the monitor. I'd like to test out how fixing those 3 bad solder joints on the underside of the board affects the problem. We also just identified that the brightness potentiometer doesn't go all the way to 0 ohms, so that might be another issue. But before fooling with that, I'd like to see how these other changes affect the display. So let's go ahead and turn it on. It's a little bit hard to gauge, but I think this actually looks a bit better. The background, the mountains, and the obstacles, I think are a little bit brighter. Since we're dealing with a brightness problem, one thing we should check is the Z signal that's coming into the deflection board. The board has X, Y, and Z inputs, and the X and Y control the position of the vector beam on the screen, and the Z is the intensity. So the Z should be between 0 and 4 volts. 0 volts is the lowest intensity, and 4 volts is maximum intensity. So what I have here is I've got the oscilloscope connected to the board, and the positive is connected to the Z input, and then I've got the ground connected to a ground lead. So if we go over here and look at the oscilloscope, what we'll see is I have the vertical scale set to 1 volt, and so we can see the Z signal is fluctuating between like 0 and up here 4 volts. So this looks like about the right range. If we change the scale to, I don't know, 5 milliseconds, we can actually see, I think this is showing like kind of each refresh cycle in the monitor. So this tells us that the voltage coming from the main boards, like the vector generator, is putting out roughly the right signal, because we're hitting 4 volts here pretty regularly. So the signal from the board looks good, and so I don't think that's a problem. So we've ruled that out. The next thing we're going to check is the B+ voltage. The B+ voltage provides the power to the flyback transformer, which is responsible for generating the high voltage needed to drive the electron beam on the CRT. If the B+ voltage is too low, it can result in a dim image. On this monitor, the B+ voltage should be between 90 and 100 volts DC. To test the B+, we've connected the positive lead from my multimeter to pin 1 on the P500 connector, which is right here. So we've got the lead connected there, and then for the ground, we're just hooked up here onto the chassis. So let's go ahead and turn on the monitor, and we'll check and see what voltage we're getting. All right, looks like we're getting 92 volts, so that's within the normal range. So I don't think the B+ voltage is the issue in this case. A new set of trim pots arrived in the mail today, and these go on the deflection board. So we've got the contrast here, brightness here, and then there's a couple linearity adjustments like right here and here. I'm going to start by replacing the brightness and the contrast. So far up to this point, we've verified that the Z signal coming in is in the correct range between 0 and 4 volts. I've verified these resistors are good. I've tested this Q504 transistor is good. This 505 capacitor is good. And then we have the contrast here. If we go down this route, I've verified this diode 506 is correct. And then we come down here, and that's where we have the brightness pot. And previously, when we measured the brightness pot, it should have gone all the way down to 0 ohms, but it stopped at around 500. So we're going to replace that and see what that does to the brightness problem. All right, first we're going to remove the brightness potentiometer. And I'm just going to set the new one on here for now. We'll solder it in a little bit. All right, now we're going to take out the contrast pot. And we'll go ahead and solder these in. There we go. And we'll go ahead and put this back in the monitor. All right, here we are after replacing the brightness and contrast potentiometers. I don't see any significant change in the brightness of the background vectors, so that wasn't the problem. Someone online suggested that this dim monitor problem could be due to poor grounding between the monitor chassis and the main boards here. So what I'm going to do as a test is I'm going to connect a wire up to the ground here on the power board, and then we're going to just clip this onto the monitor chassis. So this will create an additional ground between the monitor chassis and the main grounds over here. I've already tested continuity on the ground between this edge connector here and the deflection board. So I know that we have a ground there, but it's possible that it's not a good enough connection or something like that. So we're going to go ahead and test that and see what happens. All right, we're running here with the additional ground lead between the monitor chassis and the power board. It doesn't look any worse, but I don't think it's significantly better, so I don't think this is a grounding problem. The next thing we're going to check is the output of the high voltage transformer, which is right here inside the high voltage cage. I've taken the cover off the high voltage cage. Let's go ahead and turn the game on. And so I have the multimeter here connected up to measure the B plus voltage. So we can see we're getting about 96.5 volts on B plus. I actually turned it up just a little bit because before when we measured it, it was I think at 92, and I wanted to see if that made any significant difference, but it didn't. But so the B plus voltage powers the high voltage transformer that's in here, and then that's what produces the high voltage that goes to the anode cup here that goes into the monitor. So next we're going to do is we're going to measure that high voltage, and the normal range for this monitor is supposed to be about 14.5 kilovolts, so about 14,000 volts. What I have here is I've got my high voltage probe, and it's connected right here to the chassis, the ground. And so next thing we're going to do is go ahead and put the high voltage probe onto the anode, and we're going to measure what the voltage is there. So on the meter, we will see the amount of voltage. All right, so we're only getting maybe 5,000 volts. And that's definitely low. It should be around 14 or 15,000 volts, and we're only getting 5. So that's definitely a problem. So I think the next thing we're going to investigate is we're going to take the high voltage board out and look at it and see if there's anything we can identify as a problem. All right, we have the high voltage board here on the bench. What we have here, this is the high voltage transformer, and this is what takes the B plus voltage around 95 volts and turns it into the 14.5 kilovolts that we should be seeing at the anode. And what we just measured a minute ago was we're only getting about 3,000, maybe 4,000 volts out of this. So we definitely have a problem with the high voltage circuit here. So I've gone through and I'm going to be verifying all these parts are good on here. I previously just went through all of the resistors and measured all the values, and everything is good except this R907 over here is measuring at 527 ohms, and it should be 3,300 ohms. And it might just be that it's in circuit. So a little bit later, we're going to remove this one from the board and measure it out of circuit and see what it is. This big resistor right here is an important one. It basically keeps the voltage output of this under like a safe minimum. So if this were to get up to like 25,000 volts, then the monitor could start emitting like soft X-rays, which would be dangerous. So it's important to make sure this is working right, and this did measure correctly, almost exactly at 22 ohms. So that's good. These capacitors also, I tested those, and these all tested fine. These actually look like new capacitors. I think this has been these have all been replaced. So now I'm checking the transistors on the high voltage board. There's 4 transistors. We've got Q900, Q903, 902, and 901 here. So we'll do 900. So we go from base to collector. We got a voltage drop and a voltage drop to the emitter. If we switch this, these should be open circuits. So that is correct. If we go over here, we're going to get base to voltage drop, and going this way, we're still getting voltage drop. This should be an open circuit, but this goes to this plug out here. So the problem might be that we're measuring it in circuit. So if we take this off, and then let's see. So this is the base collector emitter. So we're going to go from the base with the positive, and we should have a voltage drop here and here. Whoops. And then the thing that was not right that we just measured was the emitter to the other terminal. So yeah, so we're getting the correct readings here. We're getting an open circuit from the emitter to the base and collector. So that means this is good, and it's just the fact that it's in circuit that is causing it to not read correctly. Make sure to get that back on there. So this one is good. Let's take a look at 902. So we're going to go from, looks like base must be in the middle, and then voltage drop. Now we go emitter to these two, so we get nothing there, so that is good. Likewise, we'll do here. That's good, and that's not good, but this could also be because we're in circuit, so I want to make a note to test 901 out of circuit. And let's see, 1, 2, 3, 4. So that's all the transistors. All appear good except possibly 901. We'll test that later. All right, I've removed Q901. So we have the positive on the base, and we're going to check for a voltage drop here and here. That looks good. And now we're going to move the positive over to the emitter, which is here. And previously, this had a voltage drop, and it shouldn't. So that's good, and that's good. So that means that this transistor is good. This is an NPN transistor, by the way. All right, we're going to solder Q901 back onto the board. All right, we're going to measure resistor 907 out of circuit. I've desoldered 1/2 of it, so now we can test it. And we're getting 3.2 K ohms, which is good. Previously, we were getting 527 ohms when it was in circuit. So this resistor is good. All right, on the high voltage board here, I've verified that all of the resistors are good, including this R907 over here, which I had to take out of circuit to get a correct measurement on. All of these capacitors are good. They also look new. All of the transistors also tested as good. So we're down to just a few more things that could be the issue. It could be the high voltage transformer here could not be putting out enough voltage. It actually puts out, I think, 29,000 volts AC on this lead, and then this goes down here to this rectifier diode that then turns it into the 14.4 thousand volts DC. And I'm hoping it's not this diode, because this is not an easy thing to replace. There isn't just a replacement part you could drop in here, but there is some part that you can get and wire it up in here, but you have to be very careful because of the high voltage. You need to have very good insulation to prevent arcing and stuff like that. So hoping that's not the problem. The next thing I'm going to do, the thing that could be a problem here is like a cold solder joint. Previously I found 3 that I fixed that were just obviously bad, where the lead was just poking through the board and there's nothing holding it there. I fixed those, but that didn't correct the problem. So I think I'm going to go through and just replace most of the solder joints on the back of the board here. So I'll just use the desoldering tool to remove the solder, and I'll just put new solder in. All right, we have the high voltage board back in the monitor. I'm not seeing any significant change in the brightness problem, so it doesn't look like the issue is due to a bad solder joint, or at least not with the ones that I replaced. So I thought we'd stop here and review what we found so far, what's been fixed, and what are some of the possible remaining causes of the dim image. The first thing I noticed when we got the monitor out was that the anode clip going into the monitor was not very secure. We could see it was partially out of the monitor tube. So we fixed that, and we got what appeared to be a slight improvement in the brightness, but it wasn't a fix to the problem. Next, we checked that the brightness and the contrast were adjusted properly. we found that even with the brightness turned all the way up, the lower intensity vector lines were still very dim. On a normal working vector monitor, if you turn the brightness all the way up, that usually results in seeing additional retraced lines where the beam is moving between vectors. We didn't see that at all here, which indicates that the brightness problem is somewhere else in the monitor. We tested both the brightness and the contrast pots with a multimeter on the bench. The brightness pot was supposed to have a range of 0 to 100 k ohms, but it measured 500 ohms to 100 k ohms. Usually missing the bottom range like that isn't an issue, but I went ahead and replaced the pot anyway just to verify. Next, we examined the deflection board and found 3 obvious bad solder joints. I fixed the solder joints, but unfortunately that didn't improve the brightness. It's actually a bit surprising that the board worked at all with those bad solder joints. In the past, there's been times when I've turned on the game and it would play blind with no image at all. It's possible that these bad solder joints could have been the cause of those intermittent failures. We verified that the B+ voltage was within the 90 to 100 volt range. It came in at 92 volts, which is good. However, I did bump it up to 95 volts just so it would be within the middle of the range. We used the oscilloscope to measure the Z signal where it enters the deflection board. On the scope, we saw that the Z signal range was between 0 and 4 volts, which is what's expected. This tells us that the vector generator on the main board is outputting a correct signal, and it's also arriving at the deflection board properly. We tested all the capacitors on the deflection board. They tested good, and they also appeared to have been replaced at some point. We also tested all the resistors, diodes, and transistors on the deflection board that are part of the Z amplifier circuit. They all tested good. We temporarily disconnected the LED at D504 to see if the XY spot killer could possibly be cutting off the Z amp. That had no effect, so that means the spot killer was not the issue. I also resoldered the Z signal wire to the deflection board just to make sure that we had a good connection there. Next, we tested the output of the high voltage transformer. That measured at only 3,000 to 4,000 volts, but should actually be in the 14 to 15K range. That measurement is very low and is most likely the cause of the dim vector lines. The real question now is what's causing the high voltage to be low. At this point, I switched the investigation from the deflection board to the high voltage board. I inspected the high voltage board and tested the capacitors, diodes, and transistors. They all came back as good. The only diode that I wasn't able to test is the high voltage rectifier diode between the high voltage transformer and the anode cup. We'll talk more about that later. I replaced about 30% of the solder joints on the high voltage board. That included the high voltage transformer, the larger capacitors and resistors, and also the P900 connector. Those changes, unfortunately, did not result in any improvement to the vector brightness. So that's what we've done so far. The obvious problem that we have right now is that the high voltage at the anode clip is only 3 to 4K. That should be in the 14 to 15K volts range, so it's significantly lower than it should be. I think the most likely cause is either the high voltage transformer or the high voltage rectifier diode is not working properly. Unfortunately, there is currently no replacement for the T900 high voltage transformer. The same is mostly true for the D903 rectifier diode. There is a diode that you can swap in, but it's in a different package, and it requires some special work to wire it up and insulate it properly. If the problem turns out to be with either of those components, then the fix here is going to be more difficult. Alright, I'm going to stop here and then continue this investigation in a part 2 video. In the meantime, I'm going to do some more investigation and also see if I can get any suggestions from the arcade monitor repair community. There is some additional testing of the voltage regulator circuit on the high voltage board that I can do. I may also swap out the high voltage board from my asteroids monitor and see if that fixes the issue. If so, that would definitely place the problem with the high voltage board. If you have any ideas on possible causes or what to check next, please feel free to comment below. I am not an expert at this type of repair and would love to get any suggestions that you might have. In any case, thanks for watching this video. I plan to follow up with a part 2 and hopefully get to the bottom of this Battlezone monitor problem.